Okay, so today's topic will be analog comparator and low energy sensing. So I will show you first what we're going to talk about through an old school example, how it was done earlier. Uh, so let's say you want to build some kind of detector that detects some switching in a sense that you have, for example, a water counter. And usually these water counters, uh, they have some display where they show the numbers 0, 0, 0, 0, 1, 2, 3, 4, and they show how many liters of water have been consumed. And now it's a modern thing to build remotely readable electronics that read the water.
Sorry, I can't see your like
Sorry, I'll click share now. Okay,
screen.
so
Yeah, yeah,
can you see now? Okay, some glitch. So
yeah. Okay.
we have water counters and they count water. And in order to make them electronically readable, most of these water counters, they have rotating parts that move these numbers ahead. And one of these rotating parts has a small magnet. So there is some disk that rotates uh, proportionally to the speed of water. It also rotates the numbers, but it also has a small magnet on it off the center. So as this thing rotates, you can put a magnetic sensor, a read sensor. We have a message in the chat. Well, this is not a rotary encoder. This is simple magnet on a disk, and it moves around. And as it moves, it passes your magnetic sensor, and when it's nearby, it closes the switch, and when it moves away, it opens it. So on each rotation, you get one impulse. So let's see, I'll draw the read switch. So usually the read switch is simply a switch in glass, and as the magnet is nearby the contacts attract to each other and make a short circuit. And when the magnet moves away, the contacts open. So on each rotation, there is one impulse. Uh, and these water counters, they usually have something like, for example, 10 liters per impulse, or something like that, or 100, or maybe 1 liter per impulse, depending on the size. So big water counters would have many liters per impulse, and smaller ones would have less liters per impulse. And these you can just buy. I'll just show you an example. So I don't know why, but in Latvia, these Zener water counters are really popular. And here, um, usually this small red thing has a magnet inside. So the magnet kind of gives an impulse. You can read it with this read switch. And you can buy separately this read switch and screw it on, and it will give you the signal. More modern ones really have some encoders, but they're more expensive. I've only seen in reality these things with a magnet on this rotating thing. Okay, so it is 0.001 cubic meter per rotation, so it's 1 liter per rotation. And how do we read these signals? So the simple way that you would find in some Arduino, for example, example circuits is this. You would have a resistor. Um, and then you would connect the read switch here on the bottom part of this, and the other end of the read switch you would connect to ground, and you would read the midpoint in the microcontroller, and the top part you would connect to VCC. So the microcontroller is here, and basically, so when the read switch is open, the pull-up resistor pulls it to supply voltage, and you read high, and when the read switch connects, you would read low. So, the output is quite simple. It's, for example, low when the magnet is next to the read switch, then it goes high, then it goes low, and you just count these impulses, and it works. And the old way would be to configure that, for example, either rising or usually falling edge of this impulse would call an interrupt in microcontroller's code, and you would increment the water liter counter by 1. So liter counter plus plus in C programming language. But here is the problem. This thing wouldn't really work very well on battery, because what if you use the water and then you go to sleep, and overnight this rotating thing stopped next to the read switch, so it's closed. The problem is, when it's closed, you get a current flowing from battery to ground through this resistor. The resistor value is something like maybe 100 kilo ohms. So if you're using probably a 3.0 volt battery, maybe 3.0, maybe 3.6, some single use battery, or maybe two alkaline AA batteries in series, so around 3 volts. So it means that this schematic, when it stops such that the magnet is next to the read switch, you're constantly consuming power. So it's 100. So it's 3 volts divided by 100,000. It's 30 microamps. And as I've said before, 30 microamps is a lot of current. It will eat out the battery within several months, maybe not in one day, but usually you would want to attach this thing next to the water counter. For example, you have a multi-story building with 30 flats. Many of them are occupied by people who are, not very welcoming to strangers, and they wouldn't want somebody to go to their flat, enter their house, enter their kitchen. Usually these water counters are under kitchen sinks, and then changes the batteries. It's going into personal space, right? So it's not good. So even if you need to change the batteries every 1 year, it's still too often. We usually want these batteries to be replaced once in 10 years, maybe, or even longer. The battery dies from age faster than from current consumption. So this is not good. So, and also, just for your information, you would also usually put a small capacitor parallel to the read switch, because there is this thing that this mechanical switch, it has some mechanical properties. As this magnet approaches the read switch, when it shuts, its wires hit each other, and for a couple of oscillations they actually hit, and because of this hitting force they jump again open and then close and open and close and open. This is called debouncing. Maybe there's a good image in the internet. So read switch bounce, or just bounce. So the contacts bounce, and so you can see that as the contacts hit each other, they're actually making some, you know, some close open moments, and microcontroller would detect a single opening and closing as maybe even 10 times opening and closing, because these metals just oscillate a little bit mechanically, and they cause these oscillations. So what is done to prevent it is you would put a capacitor in parallel to the reed switch, because when it shuts, the capacitor is discharged empty, but when it bounces, the capacitor is already empty, so there's no voltage to discharge, and these other bounces don't make any changes. And this resistor only slowly charges up this capacitor. So uh, usually you would put some like 100 nanofarads, or maybe 10 nanofarads, something like that, in parallel, so that to avoid this debounce problem, right? And the problem is that this capacitor, you would measure its size using oscilloscope. You would connect without it. You would see how many bounces you have, and then you would try multiple values of this capacitor until you find as small as possible that kind of prevents any bouncing impulses. Because if you put a very big capacitor, then every time you need to charge it, you lose a lot of current. And when the button is pressed, all this current, all this energy charged in the capacitor is lost, it's dissipated. So you don't want to put a very big capacitor there to save power again. So this would be like a regular way to do it. But if we want to improve this and make it low energy, we would do a small modification. For example, like this. We would connect the resistor to the microcontroller, and then we would write a code such that microcontroller, for example, wakes up once per second, and then microcontroller sets this line high, and then it checks out. If this point is 0, then it means that the switch is closed and it's low. If this point is high, it means that the switch is open. So you would, for example, scan this input like once a second or maybe 10 times a second. You would need to estimate this value, but once a second you set this high, read the value, and then switch this line off, so that 99.9% of the time this schematic doesn't consume any energy. And it's a big step forward. I've seen people do this, and actually you don't even need this capacitor here, because you would scan this input at lower frequency than debounce frequency. So for example, the debounce happens for 1 millisecond, so you just scan it, for example, every 2 milliseconds. So even if you got this bouncing moment, next time you'll be out of the bouncing moment. So you just scan it slower than the bouncing. So you save on this capacitor, less parts on the board. So this is an improvement. And basically it's going to consume so many times less energy as is the ratio between on and off time. So if you set it to 99.9% off and 0.1% on, then instead of 30 microamps, you will only get 0.3 microamps average current. So that's very small current. And to so this is how we can do it. And because microcontroller manufacturers know that this is a possible usage, they have implemented an automatic input scanner in some of their microcontrollers. Not all microcontrollers have it, but the idea is that if you are using microcontroller to set the pin high and then read the input and then put the microcontroller to sleep, the problem is that microcontroller, when it's awake, it consumes something like 5 milliamps. So 5 milliamps, 0.1% of the time is still, a lot of current. So what, for example, Silicon Labs and many others have done is they have introduced a new peripheral, which is based around analog comparator. So building block is analog comparator. And analog comparators can be built in such way that they consume very, very small energy. You can use them sometimes in place of analog to digital converter, because analog to digital conversions consume some considerable amount of energy. But if you only need to know whether the level of analog signal is higher or lower than some value, then you can just use an analog comparator. And the analog comparator is a triangle with two inputs. One is plus and one is minus. And if plus is higher than minus, then the output is high. And if minus is greater than plus, then output is low. And internally, one of these, well, for example, this minus, can be connected to an internal resistor divider of the microcontroller, so that it's, for example, fixed to 1/2 of the supply voltage. So anything under half of the voltage is, low, and anything above half of the voltage is high. But this is built inside the microcontroller, so I'll just draw it like this. Okay, and these microcontrollers, let's see, reference manual here, they have a peripheral called low energy sense, and they work in the following way. You can configure this thing, and it runs from a low energy clock, 32 kilohertz, so that the core is asleep, and you configure it in such a way that with some prescaler, it does the thing automatically. It automatically sets one of the pins high. I'll just, I'll probably just copy the previous thing. Analog comparator plus low energy sense. Low energy sense. I'll copy this beauty. From here, and so low energy sense can be configured in such a way that it automatically sets an input, one of the outputs high, and then compares the value and then goes to sleep, so that the microcontroller isn't even woken up. This and like this. We will do more with this in labs. So right now I'm just showing you how it's built. But in the lab work, when you receive the development kits, you will be able to experiment with this on the buttons or on the light sensor. So basically what this thing does is, after configuration, it sets some output high, then then compares the input with analog comparator to some midpoint, for example, and only if the input is high, then it calls the event for microcontroller, and then the microcontroller can increment the counter. But for the rest of the time, microcontroller totally sleeps, and this low energy sense is built in such a way that it because it does everything automatically, it consumes some like 4 microamp or even less of current. So it runs from low energy clock, sets the input high, for example, 100 times per second, compares the value. If the value is low, it does nothing. If the value is high, then it wakes up microcontroller, and microcontroller increments the counter and then goes to sleep. So you can save a lot of energy this way. Okay, it has many settings. You see this block, it's not simple. It's basic. Principle is simple, but you can do many things with it. You can set the pins high or low, but you can also set some voltage on the output. So you can use digital to analog converter to set some value. And in other microcontrollers, also current digital to analog uh, converter. So lots and lots of these things. And fortunately, Silicon Labs has good example codes so that you can take the code, modify it a little bit, and just work. And this microcontroller has internal references, and it's a little bit easier to use than might seem. Okay, but again, this is like a small preview because we will do more with this with actual programming in the labs and on our development kits here. We have, for example, light sensor, and oftentimes you have, for example, a light source that is shining on the light sensor, and if somebody passes by, the light path is interrupted, so you detect that there's no light, so somebody's in between. This is used, for example, for automatic garage door opening and closing, so you don't want to close the garage door on somebody's head. So usually it uses infrared laser beam and shines it on the light sensor. And here's the same. You don't have to actively read this input. You can just use the low energy sensor. That's one thing. Low energy, the light sensor is on the development kit. And this low energy sense can also be used to um, measure metal vicinity. So you can make an LC circuit, and this low energy peripheral can oscillate it. And if you put a metal next to this inductor, its inductance increases, so the frequency goes down, and this thing can detect that the frequency went down, less pulses per second, and it wakes up microcontroller and says, hey, there's a metal next to this inductor. So it can also be used for metal detection. And with minimal code, just configuration. But yeah. And also we should look at the current consumption of these things. So so analog comparator. Let's see, do we have it here? It's probably here. So we would want to know how much current does the analog comparator consume. As you can see, you can modify its strength of current that it consumes. It will increase its reaction time. So if you set very low consumption current, then there's a delay between the inputs going over and the output going from low to high, because very small current consumption causes the changes slower. So maybe you can't detect very fast signals, but usually the signals are slow, so you wouldn't care. um, but it's possible to change its configuration. So in low energy sense, 0.6 microamp, very small current consumption. It has some offset voltage, so you cannot measure voltages that have a difference of less than minus or plus 12 millivolts. Okay, so you can compare very, very similar signals. And yeah, and it also has a built-in resistor. So actually, you don't even need this resistor because it has several kinds of resistors built in. So you connect it like this, and because it has built-in capacitors with these values. That's pretty neat. Okay, that would be all about this low energy sensing, but